polar and nonpolar or purely polar bonds. And we started talking about bonds, polar, nonpolar bonds. And I told you before that the nature of polar and nonpolar bonds is later going to relate to polar or nonpolar molecules. And you're going to find out that in order to have a polar molecule, you first of all have to have polar bonds. Let's go back for a moment, though, and discuss what we did yesterday about the nature of covalent bonds and the sharing of electrons. Yesterday, we used two different examples. One was a fluorine homonuclear diatomic. I'll draw the full Lewis up here. We have a nonpolar covalent bond that holds the two fluorine atoms together to form a molecule of homonuclear diatomic fluorine. Okay. Bond angle of 180 degrees. Okay, because there's two things hooked together. There is no pivot molecule. It has to be straight. It's 180 degrees. Okay. We compared this kind of a bond, a single bond, with a hydrochloric acid bond. Chlorine is also a column 7A element, so it has 7 valence. It shares one with hydrogen. Hydrogen's octet of 2 is satisfied. Chlorine's octet of 8 is satisfied. And they also share 2 electrons. Now, yesterday the issue was polarity. Is there a dipole setup? Is there a positive side and negative side? Or is this an even sharing of the electrons? Okay? Are the electrons being equally and evenly shared between the two atoms that make up the molecule? And we said that the issue you need to look into is electronegativity. Electronegativity is the key to figuring out how fairly, how equally the electrons are shared. If you consider electronegativity the amount of force an atom is willing to exert in order to get an electron for itself, kind of like how strong that person is in the tug of war, the greater the electronegativity, the greater the force of the individual to pull towards itself. Okay? So high electronegativity means more force is exerted to get the electron. But it's still shared. It's just how often does an individual atom have that electron? In fluorine, we said that this is a homonuclear diatomic. There are 2 atoms. Both atoms are exactly the same. So both atoms exert exactly the same amount of force to get the electron. And by doing that, they both are pulling the same. They both get it equally. So when this electron that's being shared is in its, we think of it as orbits. This is the way it's easier to think of it this way. We know technically it's not an orbit. It's a probability location in the quantum mechanical model, kind of like buzzing like flies all over the place. But if you think of it this way, it'll help you get the concept that for every turn here, there's a turn there, there's a turn here, there's a turn there, there's a turn here. And as this electron is being passed back and forth, as one atom gets that electron, it's satisfied, but its partner feels ripped off, and so it pulls back, gets it back, and then the roles reverse. Now I've got it, I'm happy, wait a minute, that's not fair, the fluorine pulls back. And so this electron is having an equal pull from both atoms, and as a result, is shared equally between the two. Contrast that with hydrochloric acid, HCl. Hydrogen and chlorine do not have the same electronegativities. Okay? Hydrogen and chlorine do not exert the same pull on that electron. We look over the periodic table and have to decide which of these 2 elements has a higher electronegativity, hydrogen or chlorine. Now, hydrogen is higher on the periodic table. We know the trend for electronegativity is positive up and to the right. Hydrogen is higher, but chlorine is much farther to the right. And so the rightness of chlorine overwhelms the highness of hydrogen in this case. And so chlorine has a higher electronegativity. All right? While chlorine has a greater electronegativity, what practically does that mean for the molecule, or more specifically, to the shared electrons in this molecule? Where are they going to tend to be? The stronger one, right? The one that's pulling more. The one that has the greater electronegativity is exerting more force. So while the electron still is shared, it's going to tend to be at the place that pulls for it the strongest, in this case, chlorine. And so as you kind of visualize the orbit of this electron, one pass at hydrogen might mean multiple passes at chlorine before it gets pulled back, multiple passes at chlorine before it gets pulled back, multiple passes at chlorine until it gets pulled back. And the way I said it yesterday was, if we were to take snapshots, like time-lapse snapshots over here at the fluorine, snap, 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 we would find the electrons that are being shared. Occasionally they'd be here, occasionally be here, occasionally here, 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 here. And on average, we couldn't say the electron's going to be over this atom. We couldn't say or predict, hey, all things being equal, when I snap my fingers, the electron's going to be here. Because no, it could just as equally be here. It could be anywhere. On this molecule, however, if I take time-lapse photography, I'm going to get a predictable location, right? I'm going to say, you know what? As I look at this, maybe 60, 70% of the time, the electron's over here on the chlorine. If it's not equally shared, if it's over here more, then the charge that it brings is going to be on that side of the molecule. Remember, the electron is a negative charge. Overall, the charge of this molecule is a net zero. And this molecule as well, overall, looking at the whole thing, is a net zero. But remember that a net zero charge doesn't mean that there's no charges. A net zero charge means that the positives balance the negatives. So in this closed system of this molecule, and in the closed system of this molecule, we're not talking about adding or taking away electrons. We're not talking about shifting things in and out. We're just dealing with what we have. And so since we don't add or lose electrons, the charge never changes. It's always going to be balanced. It's going to be zero. However, when we look inside the system, this one over here, since the electron is evenly distributed, there is no side that tends to be more negative than the other. They tend to have the same charge. This molecule, however, the electron tends to be over at the chlorine side. And because the charge tends to be at the chlorine side, this side of the molecule tends to have a charge. What charge is that? If this is where the electron tends to be, the charge of this side tends to be negative. The electron brings with it the tendency towards the negative charge. The electron has a negative charge. The electron tends to be over here, so this side tends to be negative. When this side tends to be negative, at the same time then, this side would have to tend to be positive. And the way we note that is we use the lowercase delta, which means partial. It's a small change. You ever, like in math, use capital deltas for delta t, for example? Your slope is rise over run. Your delta y over your delta x means change or difference between. In this case, we use the lowercase delta because it's a very small change. It's something very tiny. This is a partial what? This side tends towards negative, right? Partial negative. This side of the molecule tends to be partial positive. Over here, I can't do that because it's equal probability it's going to be over one or the other, so I cannot say it has a partial charge. This one I can. Again, the electron tends to be around the chlorine, which means that side tends to be partial negative. Now, right now I'm using a molecule to explain a single bond, right? In a moment, we're going to look at molecules that are based on tetrahedrons, which means they have four bonds, 3 bonds, 2 bonds, different geometries. Right now, I want you to think about this bond between the hydrogen and chlorine. To write it below all my circles now. The bond here in the middle. Yes, I'm considering this molecule, but what I'm really considering is this bond between the hydrogen and chlorine. In this bond between the hydrogen and chlorine, we said the electron tends to be on what side? Chlorine side. The way I can indicate that is I can take my bond and I can draw an arrow head on that side to indicate that the electron tends to be over there. Okay? And then I can also, because the electron tends to be over there, that makes this side positive. Okay? So this is the next evolution in your Lewis diagrams of showing the polarity of the bond between them. The polarity, the direction of the partial. In this case, chlorine is partial negative. The electron that's shared tends to be over there, and when it's over there, it makes this side positive. Now, as the book will tell you, there's different texts that do it different ways. In some cases, they may actually just go ahead and still show the bond and then put the symbology below it. Okay? I tend to replace the symbol with the arrow. So I don't want you to get confused. Mine will tend to look like this, meaning there's a single bond with a polarity to it. Some text will say, here's a single bond, and oh, by the way, this is a separate arrow showing the polarity of that bond. Hopefully you're savvy enough now to look at this and go, wait, hydrogen and chlorine, there's not a double bond between those two. It's a single bond. This must be a case where they show the bond and then they show the polarity of the bond. Right here. Let's go ahead and look at the example on page 190. That's example 5.3. This is showing identify the polar bonds and determine the charges that result from an ammonia molecule. Page 190. 190. Ammonia. So to figure out the polarities and the charges, we have to first of all start with a good two-dimensional Lewis diagram. The molecule is NH3. Now, a long, long time ago, when you barely understood this stuff, like 2 weeks ago, you had to sit down and say, okay, I'm going to draw my nitrogen, I'm going to put 5 dots around that, I'm going to draw my hydrogen, put 1 dot around that, and I'll take the one that has the highest number of unbonded electrons, so that would be my nitrogen, I'll put that in the center, and I'm going to take the 2 unbonded pair electrons and put them at the top, right? That's kind of where we would have done. So at this point, we're just going to go ahead and go, oh, it's nitrogen with 3 hydrogens. It's going to look like this because I'm going to put my unbonded pair on the top. There we go. There's my two-dimensional Lewis structure for ammonia. Now, looking at this molecule, ask the question, are there differing electronegativities between the atoms involved? Notice there are no bonds from hydrogen to hydrogen, right? If we did have a hydrogen-hydrogen bond, what would the net polarity of that bond be? Neutral, right? There is none because they equally pull back and forth between each other. But we have different elements involved here. We've got hydrogens, 3 of them, bonded to a nitrogen. Hopefully now you're realizing, hey, if I look at the one case, it applies to all 3 cases. I only really need to consider one bond, and that is a covalent nitrogen and hydrogen bond. Now, we're balanced, 2, 4, 6, 8, 2, 2, 2, we're good. Where is the polarity? Where will the electrons tend to be? We know that because they're not the same element, there's going to be a difference. So the electrons that are being shared between a hydrogen and a nitrogen, are they going to tend to be around a hydrogen or going to tend to be around a nitrogen? Hydrogen's over here on the left high, nitrogen's way over here on the right. Okay? So in this case, the electrons are going to tend to be towards the nitrogen. Yes, hydrogen is higher. Nitrogen is way farther to the right, and that overwhelms the highness from one column. So we're going to say that the electrons here are going to tend towards the nitrogen. How would I indicate that on this two-dimensional Lewis structure? How would I show that the electrons are favoring location toward the nitrogen? Take my covalent bonds, put arrowheads on them towards the nitrogen, right? And complete the modification with what other symbol? Right, putting the line, which think of as a plus symbol, toward my hydrogens. Okay? Now in the book, they say they don't add it, but yet they do. You know what I'm saying? They say they're going to just modify the symbols. But if you notice on the top of page 191, they have a hydrogen, or 3 hydrogens and the nitrogen there, and they've modified it by having the bond and then also putting the symbology on it. So hopefully if you looked at the top of 191 there, you wouldn't get confused and say, oh, wait a minute, my nitrogens and my hydrogens are connected by double bonds. No, they're not. They're single bonds. You should know that, right? A double bond would mean that hydrogen would have 4 valence electrons. It doesn't have 4, it only needs 2. So you're going to need to be a little bit savvy on, is this a double bond with one of them being symbolized, or is it one with a symbol beside it? Sorry, that's just because there's 2 standards. They go back and forth. So we're not talking right now on whether or not, I want you to understand the difference. We're not at this moment trying to determine whether or not ammonia is a polar or nonpolar molecule. We'll talk about that in just a moment. All I'm looking at right now are the bonds that make up ammonia polar or nonpolar bonds? In this case, we'd look at it and say what? Are they polar or nonpolar? Remember, if they're polar, that means the electron favors one over the other. There's a pole. There's a charge. If it's nonpolar, that means there's an even sharing. There is no positive and negative side. It's balanced because it's shared equally. So in this case, again, are these polar or nonpolar bonds? They're polar bonds, right? If you draw the arrowhead and the plus sign, it's a polar. If it's nonpolar, there's no symbology to put there. When I draw hydrogen to hydrogen as a homonuclear diatomic, there is no arrow or plus. Why? Because the electron is equally over either one of them. There is no symbols to put on here. This would be a nonpolar bond. These 3 indicate a polar bond. When I look at that, what I'm saying is, oh, the electrons that are being shared between hydrogen and nitrogen, they tend to be at nitrogen. If I go into this neighborhood and I start knocking on these doors, there's a child catcher, right? I'm trying to find the kids. Where are the children? Oh, they're over at nitrogen's house. Why? Because nitrogen tends to be like the Kool-Aid mom on the block, right? That's where all the kids go. They go to nitrogen. You want to find the kids? Go to nitrogen. You want to find the electrons? Go to nitrogen. Why? See, nitrogen has a stronger pull. Kids don't want to stay home. They want to go down to the Kool-Aid mom's house. That's where they want to be. If I'm looking for the electrons, they're going to be around nitrogen. So nitrogen is hoarding the electrons. Occasionally they'll give a nod and say, okay, you can go home for lunch, but come right back. Yeah, go home for dinner, but come right back. Go home and spend the night, but guess what? Tomorrow morning, they're going to be right back. Okay? So the electrons tend to be where the arrowhead points. The arrowhead points towards the element with the highest electronegativity. Why? The electronegativity of that element has a greater draw on the electrons. That element is using force to pull the electrons to themselves. They're hoarding the electrons. It's not fair. You and a friend go in on a car together. You decide you go into this relationship with your friend thinking, oh, we'll go in this car together, and I'll have the car on Sunday, they'll have them on Monday, and I get Tuesday, they get it Wednesday, I get it Thursday, they get it Friday, I get it Saturday, they get it Sunday, which means I get it every other Sunday, every other Monday, every other Tuesday, right? But what really happens? One of the friends doesn't play fair, do they? Oh, I need it on Friday. Yeah, okay, so can I have it Thursday? No, but I've already got plans for Thursday too. And they kind of keep it more than their fair share. And usually in those relationships, one of the friends will be stronger, and one of the friends will tend to be a little more passive. The passive person loses out, the stronger-willed person gets it. Nitrogen is the stronger-willed friend. Nitrogen is getting it more often. Even though it's supposed to be fair, it's not. Nitrogen is getting it more often than hydrogen does. And because of that, nitrogen is going to tend to be what charge? Negative. Because it tends to have 1, 2, 3 electrons. It's going to be strongly negative towards the center of the molecule and positive towards the hydrogens, right? Because the hydrogens are going to tend not to have any electrons around them because they only have 1. Nitrogen's stealing but 1 they have. And so in this molecule, it's going to tend to have a partial positive, and a partial positive, and a partial positive. And in the center, I'm just going to draw it once, but it's going to tend towards partial negative in the center. Nitrogen is going to tend to have these 3 shared electrons. Does hydrogen ever get that electron? Actually, their own electron plus the other one? Do they ever see it? Yes, they do. But if you take a snapshot, where would you expect to find it, the electron? At nitrogen. Okay. You can see on the example as well with the CF4 molecule, C2F4. See the double bond between the carbons, and there is no symbology on those two carbons. Those two carbons, when they are sharing electrons, are sharing them equally, which is why there is no additional symbology to the bonds between the carbons. But when you look at the fluorines and the carbons, you've got carbon, and you've got fluorine, right? Fluorine is to the right of carbon on the same row. It's to the right of it. So you would expect the fluorines to have a greater electronegativity to pull those electrons. Now look at the last diagram there on page 191. See, the arrows are showing that the electrons are tending to be at fluorine, making the carbons tend towards positive. There is a partial charge of negative towards the fluorines and positive towards the carbons. We good with that? Okay. Now we take this idea of polar and nonpolar bonds, and now we're going to apply the whole thing to the molecule. We're not going to go into this deeply today. We'll do it tomorrow. But here's the idea of what we're moving toward. I need to go and draw a two-dimensional Lewis structure, maybe even the three-dimensional Lewis structure. And all we would do was take the same thing, the NH3, for example. We'd go N, we got a double, we've got hydrogen. We then have a hydrogen here and a hydrogen back. My shape is based on a tetrahedral, or tetrahedron, but it's not a tetrahedral. It's a pyramidal, bond angles of 107 degrees. Good. And my electrons are tending towards, now in this case, you need to draw the symbology, right? My electrons are tending towards the nitrogen. The first step is going to be to figure out the individual polarity of the bonds in your molecule. What is the direction of the polarity in the bond? Now that we've looked at each individual case from the context of this hydrogen and this nitrogen, this hydrogen and this nitrogen, and this hydrogen and this nitrogen, where does the electron tend to be? So that's the first part of it. The second part of it is to step back and look at the whole thing and say, oh, does there tend to be a charge on the molecule as a whole? Polar, nonpolar bonds help you determine whether or not you have a polar or nonpolar molecule. And the polarity of the molecule is the sum of the polarity of the bonds in the molecule. Quick case. I said right here that this is going to tend towards having positives at the hydrogens, right? This is going to tend towards a partial positive, partial positive, partial positive. Now, look at the molecule as a whole. Do you see a balance or an imbalance of the forces in this molecule? What would you need for it to be balanced? Well, I'll give this one to you. We would need a tetrahedral, and it would be more like a CH4 molecule. Let's say we had a CH4. Let me draw it in 2 dimensions because we know that the geometries work in 3 dimensions as well. But in 2 dimensions, hopefully you would see that between a carbon and a hydrogen, the carbon's going to have a greater pull than the hydrogen. The electrons are going to tend to be moving in that direction. And if I said, what is the net charge on this molecule? Do you see that all the charges of all the bonds are equally distributed and pulling in opposite directions? So if I have equal but opposite forces, what is the net force? If equal but opposite, the net is neutral, nothing. So in physics, when you add up your vectors here, the net vector of all these different pushes and pulls is going to be 0. They're going to cancel each other out. And when the geometry allows the forces to balance each other out, the molecule then does not have a pole. It's balanced. I can't go through and draw a line and find an imbalance. But with a molecule like this, if I draw a line right here, what do I have? I have a very positive part of the molecule and a very negative part of the molecule. So this molecule has a pole. And so each bond here is polar, and the molecule as a whole is polar. And we're going to find that in order to have a polar molecule, you have to have polar bonds, and the polar bonds cannot be equal but opposite and balance each other out. Pick it up tomorrow.